the line segment from P 0 to 1. So this distance and this distance is the same. And then you go to P2 in the same way. So you could do this with a smooth shape or polygon, as I've done. And this has been studied by a number of people, and I think maybe the main question was whether you could ever have unbounded orbits, whether you could make a shape and a point, and you could go around and eventually leave every compact set. And Jürgen Moser thought of this as something like a question about this system is like a toy model for planetary motion. And this question about unbounded orbits was something like, the stability of the solar system in this model. So there were a number of theorems about this, none of which I'm going to talk about except mine. I finally proved that you can have unbounded orbits. So if you have a kite, and if you look at the group generated by the 180-degree rotations in the vertex, and if that group is indiscrete, then there's unbounded orbits.
So is the kite just a quadrilateral, or is
a kite is a quadrilateral with a bilateral symmetry in this way, where one of the diagonals is open. The next year, Dolgopia and Fayad showed that for the semi-disk, there are also unbounded orbits. So those are more or less the only known examples to date. So I after proving this result, I spent a long time trying to think about how could I prove something like this in general, like maybe there's almost always unbounded orbits or something along those lines. And eventually I got tired of this and I veered off into this other thing, and that's what I'm going to talk about. But it turns out that the other thing looks kind of superficially different from outer billiards, but there's some underlying connection. So now for the thing I'm really going to talk about. So I'm going to talk about square turning maps. So a square turning map is, there's a one map for each real number s greater than 0. And this is supposed to be an infinite grid of squares in the plane where the vertex is the origin is the vertex of the square, and the side length of the square is s, and the sides are parallel to the coordinate axis. Then the map G sub s turns each square clockwise by 90 degrees. So you can see the action of G sub s. Now, this map is not so interesting dynamically or algebraically because G sub s to the 4th is the identity. But you could imagine, you could look at the group generated by, say, G sub s and G sub t and G sub u, etc. And you could say, well, what's this group action like on the plane? What does it do to the plane? And in particular, I'm going to look at the word G sub s, G1, GS, G1, GS. And if you did GT, if 1 was replaced by t, you could just rescale it so that t was equal to 1. So, and the reason why you might want to look at words of length 4 or words of length divisible by 4 is that the linear part of this map is the identity. And so this map is a piecewise translation. If you were to use words whose length wasn't divisible by 4, then you'd get something that wasn't a piecewise translation. So I like this one because it's, you might say, why not just do G1, GS, but somehow that thing linearly rotates 180 degrees. So I like this map better.
What's G1?
G1 is when S is equal to 1. So it's the rotation in the unit square grid. So you're taking two different size grids, and you're first rotating one, and then you're rotating the other. And then you pick your point. You pick your point, and you. I'm sorry. You pick your point and you locate it in the S grid, and wherever it is, you find the square that contains it and you turn it. And next you see where you take that new point and you see where it is in the grid, in the one grid, and you turn it, and so on like that.
S is a number here.
S is a number. S is a positive number. So S is the side length of the square.
S is the side length of the square.
Yeah. So this is an infinite grid of squares. It's supposed to represent an infinite grid of squares in the plane. And it's the tiling of the plane by squares. Yeah, so if you have a square tiling of the plane, there's only one thing you could really ask, which is like, what's the size of the tiling? What's the size of the squares? And S is the size.
So you mean the squares don't have the same size?
They all have the same size. G sub s is defined relative to an infinite square grid where the side lengths of the squares are all s. And then G sub 1 is defined relative to an infinite grid where the side lengths all have.
These are conjugate by the monothecy or something like this. These maps are conjugate by the monothecy or something like this.
Yes, exactly.
Right.
Right. G sub s and G sub t would be conjugate by the homotopy, the homothety, which dilates by s over t. Or something. So all these maps are conjugate to each other.
I'm sorry, I just missed the definition.
Okay, so
All the grids contain the origin.
Take a point x, y.
yeah, take a point in the
Divide x and y by, I mean, just find the, you know, the greatest integer in x over s and y over s to figure out what square it lies in, and then take that square and rotate it.
Yeah. Right, so
Take
you,
just one square.
They rotate all the
Well,
squares,
right,
but
you rotate all the
for that
squares
particular
simultaneously.
point, only the square that it's
Right.
located in is gonna matter.
right,
So okay, so it's a rotation by pi over 2.
yes, in each square separately. The map's not defined on the edges of the squares. It's a piecewise isometric map of the plane.
Ah.
But it's not everywhere defined. It's not defined on the one skeleton of the squares.
Okay, and you just rotate this
Yeah, you do each one separately.
specific square.
Well, you do them simultaneously. In other words, G sub s turns every single square of this. Okay, so
I can do a picture, look.
let me draw a picture. Yeah, let me draw a picture.
You cover your bathroom with tiles, and then you go
Okay,
in
so-
and turn each tile around.
Yeah, same.
The same,
Okay, so I have a point. What do I do to this point? I move it to here. So this is the point x. This is the point G sub s of x. And this is the point G sub s squared of x. And this is G sub s cubed of x. And then back to x.
And okay, and so S, what is S?
S is the side, this is s. So in each square, what's a translation mean in my language? You would take the plane and you would pick it up and you would move it over by some vector. And what's a rotation in my language? You would take the plane and you would just turn it about some point. So in this language, you would take all the individual squares in this grid and you would turn them all by 90 degrees. So it's a piecewise rotation.
But I just don't get why it depends on S.
Because
on the square.
imagine the grid was twice as big. Imagine it was 2s. Then this whole square would just move like this instead of individually. So in other words, what you do to the point depends on which square grid it's in. And if the square grid is imagine S was a trillion, then you'd be taking this enormous square block and you would just be moving it. So you couldn't even tell it was a discontinuous map. But if S was like 1 over a billion, then all these tiny squares would be rotating.
You move all squares, right?
Yes, yeah. Okay. Right. I don't know why the projector's having some problems. Okay, so let me just show this.
It's when your computer gets quiet.
Yeah. So, so this is an example that the checkerboard, the green checkerboard is the grid of side length 1, and the white squares are grids of side length 7 over 11. And so what I'm drawing is the orbit of this point under the map. This point, I do this map G1, GS, G1, GS, and it goes to here, and then to here, and then to here. So this point is a point of period 6. Okay, so actually, so see this red rectangle has the property that every single point in that red rectangle has the same, has a period of the same size. And what's going on is that if you have a little set the map does the same thing to the set, provided it's in the same square. But if the image of the set slops over two of the squares, then there's a kind of a parting of the ways. One part of it goes up and the other part goes down. So this rectangle has the property that as it moves around, it doesn't, I mean, I think I can draw the whole thing. Yeah, like this rectangle, you can see that it sort of never crosses any of the squares. If you tried to make it any larger, then it would cross. And so if I picked a point outside the rectangle and I did the orbit, I'd get something else. You know, who knows? I'll get other orbits. So these regions, these are called I call them periodic islands. These are the largest regions which everything in the region has exactly the same orbit. So they're kind of maximal domains of continuity for the map.
And they're always rectangles.
Yeah, they're always rectangles because the conditions are basically, do they cross over the sides of these auxiliary grids? So let me erase everything. And now I'm going to draw something else. What I drew now, rather than draw the orbits, what I drew are just the periodic islands. And there's something interesting about the pattern. If you look at the continued fraction expansion of 7 over 11, it's 1, 1, 1, 3. So it's 1 over 1 plus 1 over 1 plus 1 over 1 plus 1 third. And if you look at the tiles, you see there's one long one that goes across. So there's 1, 1, 1, and then 3. So the pattern matches the continued fraction. So I'll try to pick another number. I'll pick a random number. I can do that. Try to remember. I pick a random number. Okay, 71 over 92. So I send it. I draw the picture of the periodic islands. Let's check out the continued fraction expansion. Okay, so it's 1, 3, 2, 1, 1, 2. Okay, so it works. So I'm going to try to develop enough theory to prove this result. I can't quite prove this result. Okay, I don't know how to prove it, but I'm going to give you enough. I can explain sort of. I developed some theory to try to understand like why this thing happens. Let me explain why it's hard to prove. What the difficulty is. Which like let me do a nice example. Okay. Let's pick a nice one.
So the input is the ratio between S and T?
Yes, but I just normalize so that T is 1.
Yeah.
So this one's nice. This is 1, 1, 1, 1, 1, 1, 2. So this is a nice picture. Kind of infinite tennis court. Let's see what the orbit looks like. So I'm going to pick up my favorite. Let's see. Let me track the orbit. Here's the orbit. Wait for it. Wait for it. Okay, so this suggests that like as the continued fraction expansion gets longer, this thing is becoming like a large-scale fractal. So what makes this theorem difficult to prove is that in order to describe these tiles, you have to describe longer and longer excursions. And so there's sort of like an unbounded amount of information you have to somehow control to see what's going on. So, okay, so that's one thing that makes this hard to prove. I don't know how to prove that. You would guess that somehow that you could take a rescaled limit of this as the parameter. Well, the parameter is supposed to be close to 1 over root 2. S is converging to 1 over root 2 if you let the.
Sorry, so again, on the definition. You
Okay.
have 2 checkerboards. Right?
Yes, and one of them has scale 1, and one of them has scale S.
But then they have
Okay.
not placed at the same point.
They are. The origin is a vertex of both. Right.
But on your picture, it looked like you had 2 checkerboards. I mean, you had one checkerboard and then you had another grid. You had-
Well, okay, so
you had the blue-
the solid checkerboard has side length 1, and the white checkerboard has side length, 1/√2 approximately.
They don't have the same base.
They do, right there.
Oh, they do, okay.
I mean, you could, okay, so you could say, well, what happens if they didn't have the same base point? And, in the irrational case, you more or less, as you move around the plane, you see every possible offset. So that's not so important. But this is somehow it makes, okay.
So in your argument, you seem to imply that there is some continuity when between the parameter.
No, I mean, I'm not claiming that, it's just an experimental observation. If you put more twos, you'll see the thing seems to grow. Yeah, I mean, there's no explanation yet, although I'm gonna explain it to some extent. So the other thing I want to say is that the pattern's not perfect. If you inspect it closely, you'll notice, like, for example, over here, like this sort of wants to be like the other ones. And this isn't a computer error, this is really correctly computed. So somehow this is like a kind of a beautiful pattern with flaws, I'd say. So I'm going to try to explain the flaws as well. Okay. So, all right. So again, the system, the map, G sub S for any S is just this square turning map, and then you're looking at the group generated by a bunch of different ones, and I'm taking a particular word and I'm studying its dynamics. Okay, so let's get rid of that. Go back to the talk. So for some context, so an IET stands for interval exchange transformations, and these things have been studied for 50 years quite extensively. And what you do is you take an interval and you chop it up into a finite number of subintervals, and then you rearrange the pieces according to some permutation, and you just slide them back together so that they fit in the same interval. One place where you see these things, where you might see them, is like if you, if you have one context is like if you have a measured foliation on a hyperbolic surface, a measured lamination, and you take a transversal and you flow around and then you come back. The return map will be an interval exchange transformation. Another place people study these things is in rational billiards, or in flat translation surfaces, or for quadratic differentials on Riemann surfaces. Anyway, these things are kind of closely related to type noise theory and a lot of things. A pet. So what a pet is, it's a generalization. What it is you have two polygons. This is probably not the first one you think of. They're not so easy to construct, but you have two polygons and they're partitioned into smaller polygons in the same way, same pieces but in different places. Like, for example, this piece here, it has a copy that's translated over to here. So each piece on the left has a translated copy on the right. It's sort of like a puzzle that you can rearrange a different way and get the same polygon. And then this implicitly defines a map from the domain to itself. You just take each point, you see which piece it lies in, and then you translate it over to the new location.
The one on the right isn't just a reflection of the one on the left side.
No, it's not.
It's very close to that.
Yeah. Even if it was it might be, okay, so it might be the reflection.
Of the vertical axis, yeah.
It might be the reflection in the vertical axis.
Yeah.
But that's not the map I'm talking about. I'm talking about the. Yeah, I think probably it is the reflection. Yeah, good eyes. Anyway, but that's not the map I mean. It's a special thing. It has a property that any piece also has a translated copy, and so the translated copy is non-trivial. There was a classic example of a dynamical system studied by Adler, Kitchens, and Tresser many years ago, and this thing somehow is equivalent to that, for what it's worth. Okay, so does a pet make sense? What it is? It's literally it's like an exchange of polygons. Anyway, so these things are like the square turning maps in the sense that they are. I mean, the square turning map. If you look at my particular word, it's a piecewise translation. And it is a pet defined on all of R2. So you could also have R2 partitioned into pieces. And also outer billiards, not the map itself, but the square of the outer billiards map on a polygon is also a pet. So pets are sort of common to all these things. So there are some operations on pets. So the first one is called renormalization. And the way I'm explaining this a little bit sparsely, but you have some dynamical system on F on a space X, and you have some subset A in X, and you look at the first return map to A. And then suppose you have a new dynamical system Y in a map G, which is conjugate to the first return map on A. Then you would say that YG is the renormalization of XF. So the classic case of this is you have a circle rotation. So you have a point, and you just start rotating it around. And then, so the big space is X, and the small space is A. And you just wait till you pick the point P0 and P1, and then eventually you're going to return to this interval. And you think of Y as just A with the endpoints identified. And then there's another circle rotation which is conjugate to the first return map of this rotation on A up to where if you worry about the endpoints you'll go crazy, but if you up to say finite number of points there's a conjugacy. So whenever you have an irrational circle rotation, you can take this interval and then there's a smaller interval and then you can renormalize it to get another rotation and you can repeat. And when you do this, you're more or less computing like the continued fraction expansion of the rotation number, but not quite. There's some fudging you have to do. There's something general like that. If you have a general IET, you can look at the first return map to all but the last interval, but you might not look at all. Maybe you look. I mean, there's four choices you can make. You either look at the first return map to all but the last, you look at the first return map to all but the first, or you take the inverse map and you do that. This is called rosy renormalization or rosy induction, and this is the thing that's related to like the Teichmuller flow. So there's this kind of classical. There's this really nice renormalization. If you take an IET with n pieces and you do this rosy renormalization, you get another one with n intervals. So the rosy renormalization gives you this kind of self map on the space of all n interval IETs, and in a sense, this is a kind of a model for the action of the Teichmuller flow on the bundle of quadratic differentials over Teichmuller space. But I'm just wanted to say that there's some context for renormalization. It's a big subject in dynamics. But anyway, this is what you do. If you have a pet and you have some polygonal region, and you look at the first return map, you'll get, often you'll get another pet. You might get something where it's broken up into infinitely many pieces, but often you get another pet. So that's what it means when one thing is a renormalization of the other. Geometrically, what it means is that if there's lots of periodic points, you have this kind of tiling by these periodic islands, these kind of maximal regions where everything's defined. And when you have renormalization, basically the tiling you see in here is just similar to what you see in here. So H is supposed to be like a similarity map. So one hallmark of renormalization is that you look at one system and you see on a small scale the other system on the kind of same kind of tiling you see in the other system. So it's a kind of a generalization of self-similarity. Okay, so the other operation I'm going to talk about, this one is something I made up myself, but probably it's been studied lots of times. It's an affine compactification. So the way it works is that you have along the top you have a pet, think of an unbounded pet of low dimension, like 2. And on the bottom you have some other pet, like where Y is supposed to be like a higher dimensional compact space, and G is some other map, and then a compactification would just be a commuting square, a locally affine map from X into Y, which makes a conjugacy between the action of G and the action of F. So let me try to explain what this means. Imagine this is supposed to be a polygon exchange map in a square. So just think about this example. You have a polygon exchange map in a square, and I take the line and I map it into this square as some kind of irrational geodesic. And imagine something lucky happens in that my polygon exchange transformation preserves this infinite geodesic. then this infinite geodesic intersects all these polygons in an infinite list of intervals. And when I do the map, it just moves these intervals around. So the action on the higher dimensional compact thing induces a kind of infinite interval exchange transformation. So this is a very general kind of thing. You could imagine you have well, what's special about this is that this map H is supposed to be locally affine, or, in fact, locally in isometry. But you could imagine the following kind of thing, where you have a dynamical system on an unbounded region, and you can define what you mean by the dynamical topology, which just means that like two places in the unbounded region are close topologically, or if the dynamic sort of looks the same in both regions, more or less. And then you could complete with respect to this topology, and this would maybe give you a compact thing and a dynamical system on a compact, say a higher dimensional compact thing, which kind of induced the dynamics on the lower. So why would I be interested in this? Well, I've got this unbounded system, and I've got these long orbits, and I can't see them all. So I want to compactify the space, and then have sort of be able to look at the orbits in a compact space and see what's going on. Okay, so I've described two operations. I've described compactification and renormalization. And the punchline of the talk is that, more or less, is that I'm going to take my square turning map and I'm going to do a compactification and then renormalization. I'm going to show that it has renormalization. But it's not quite going to work, but then I'm going to get it to work. Okay. So far so good? Okay. So I'm going to describe now a construction of pets. So first, this is just preparation. So imagine you have a lattice in a vector space, and also a polytope, which is a fundamental domain for that lattice. So here, this region F is supposed to be a fundamental domain for the usual square grid. Of course, each square grid has many fundamental domains, and each fundamental domain is a fundamental domain for many lattices. But anyway, if you have one, there's a map from the plane into the fundamental domain. It's just the canonical map. You just add vectors from the lattice until you get into the fundamental domain. So this is a way of mapping. Anytime you have a lattice in a fundamental domain, you get a map from the vector space into the fundamental domain. So now I want to describe what I mean by a double lattice pet. So the situation is that you have two lattices and two fundamental domains, and two lattices and two polyhedra. And both polyhedra are fundamental domains for both lattices. So I'm not saying you can do this, but let's just say you could. So if you could do this, firstly, there's a map from F into F2. You just add lattice vectors from L2 to get into F2, and then you go back to F by adding lattice vectors in L1, and this gives you a pet defined on F. More generally, you could have a graph that was decorated by the vertices can be assigned polyhedra and the edges can be assigned lattices, so that if a vertex is incident to an edge, the polyhedron is a fundamental domain for the lattice. And then if you pick a base point vertex, then there's a homomorphism from the fundamental group of the graph into the group of all pets on the domain, because every time you take a loop, you get a map. So this is kind of the simplest case of that kind of tutorial.
Which means that you take any element of L1, which is a translation, right? And compose with the element of L2 that brings you back in the fundamental domain.
Not exactly. So let me say it like this. You start in F, then there's a unique, F includes in the vector space, so there's a unique element of it, say L2, that maps you into F2. And then there's a unique element of F1, L1 that maps you back into F. Right. That's right. So when you draw a picture like this, it's assumed that everything in sight belongs to the same vector space. Okay, so I'm going to give an example. So my example comes with a parameter S. And you take this parallelogram up there where the angle is pi over 4, and the bottom side is, well, the base is 2 and the height is S. So So F1 is going to be that parallelogram and then centered at the origin, and F2 is the one that's rotated 90 degrees, and then the lattices are spanned by the edges of the reflections of those parallelograms. And these four parallelograms, this picture I drew down here is supposed to show how all of these parallelograms fit together in a single diagram. And then it's a little lemma that this L1 is F1 is a fundamental domain for both L1 and L2, and likewise F2 is a fundamental domain for both L1 and L2. So I wrote a book called The Octagonal Pets, and this example is the octagonal pets. It's a one parameter family of double lattice pets. Okay. So let me tell you the main theorem about this. So I call it the octopet renormalization theorem. So R of S is this map. The Gauss map, there's a more familiar map, but gamma of S is 1 over S minus the floor of 1 over S. This is the Gauss map, and it's the thing that generates continued fractions. And the R map is like the Gauss map, and the Gauss map is closely related to the modular group, or to the 2-3 infinity triangle group. And the R map is related in the same way to the 2-4 infinity triangle group. So my theorem says that if you have parameters that are related by the R map, then the one system is a renormalization of the other. So in other words, it works like circle rotation or like the Rosen induction. And I'm illustrating this with a picture. On the top, this tiling you see here. It's the periodic islands for this pet with the parameter 5 over 13. And down here, this is the periodic islands for the parameter 3/10, which is R of 5 over 13. And you can see that if you look at the tiling up here, it's just a similar copy of the piece over here. So the first return map to these colored regions up here is conjugate to the first return, or I could say like this, like the first return map to the left side is conjugate to this first return map. So that's my theorem, one of my theorems. For any given parameter, there's a proof by inspection, right? But then, okay, here's another example. Here's the parameter 8 over 13, and the first return map to the red pieces up there is the same as the first return map to the red pieces down here. So this theorem, it sort of lets you understand like what's happening for more complicated rational parameters based on what's happening from simpler rational parameters. And this theorem, there are some sample corollaries, like you can tell exactly which shapes appear as periodic tiles. And another thing I proved is like the set of aperiodic points has positive codimension. So in other words, almost every point is periodic. And then I proved that, well, the 2-4 infinity triangle group acts on the parameter space by Mobius transformations, and then for parameters in the same orbit, the tilings are locally similar. So in particular, the Hausdorff dimension is invariant under the action of the 2-4 infinity triangle group. And the 2-4 infinity triangle group acts ergodically on the parameter space, so the Hausdorff dimension of the aperiodic set is almost everywhere constant independent of the parameter. So these are the kinds of things you can get from this theorem. Maybe I'll say a tiny bit about the proof. Yeah, for each parameter, it's a finite calculation. You just can check that it works. So what I do to prove the whole thing, roughly speaking, is I make a 3-dimensional space, which is just like a fiber bundle, where over each parameter I have the dynamics of that parameter. And this turns out to be a piecewise affine map. And so in a sense, in the 3-dimensional thing, it's still a finite calculation. Okay, I mean, that's not much of. I don't really understand why this is true. I discovered it on the computer, and then I just found a proof. Okay, so now let me just give more examples of pets. And again, I found these experimentally, but you just define these matrices for any. So these are the first example is 4-dimensional, 2 complex dimensional, and 4 real dimensional, and then the next one is 12 real dimensional, and then 20 real dimensional, and so on. So these are kind of high dimensional pets. And you take these two, you take these matrices A, B, and C. C has parameters, but A and B don't. And then you just, the fundamental domain, the polytopes are just A plus or minus times C of the unit cube, and the lattices are B plus or minus times C of the Eisenstein lattice. And then it turns out that these things are, they're always a double lattice pet. So this is an infinite family of these things in higher and higher dimension. And okay, they look crazy, but if you take n equals 2, and you just set s equal to lambda 1 over lambda 2, then this is this 4-dimensional thing. And there's one invariant, there's actually 2 invariant slices that look like the previous example at parameter s, and then another 2 slices that look like the previous example at parameter s over 2. So in other words, this algebraic thing is a 4-dimensional thing that contains this octet that has the renormalization theorem. Okay. Okay, so here's the theorem. You take any word in these square turning maps, and then you take the square of the word. So the simplest case would be like G1, GS, G1, GS. And then if the word is like them, then this unbounded system has an affine compactification, which is one of the ones in the family. So in other words, I said before, I've got this square turning map and I want to compactify it. So if you do the one I like, G1, GS, G1, GS, then it has a 4-dimensional compactification. And I'll just go back and show you what I was talking about. It's this here is, F is the square turning map, and then G is this algebraic thing that I define in terms of matrices. And then I'm going to tell you the formula for H. So H is just literally this map. And then you just check that all the words, all the generators of this group extend. And so then you analyze the singular set, and you cut open the torus along the singular set. The image is a torus. You cut the torus open, and then you see that actually it's a parallelepiped. And then you just analyze what the map is, you change coordinates, and you find that you've found the algebraic sets. So the punchline is if you do the square turning map, it has a 4-dimensional compactification, and that 4-dimensional compactification has an invariant slice, which is this renormalizable system. Okay.
Why just for those numbers?
I don't know. It just yeah, that's a good question. I mean, it's just an artifact of the proof. I mean, if you yeah, so why doesn't yeah. So it doesn't so that's a good, I can't answer that question actually.
Because they're doubles of primes?
Well, they don't do doubles of primes, they're just doubles of odd numbers.
Yeah.
I mean I just okay, so I think maybe for the other ones they do have compactifications, but I couldn't work out what it was. I couldn't get it into this family or something. But anyway, I just care about the case n equals 2, really. Just that's the case of this square turning map. Okay, so the next theorem is a little bit of a digression, but I just want to say that for outer billiards, if you take a polygon and you can look at a first return map to a strip that's defined parallel to an edge, and it's twice as wide as the polygon is tall, then this thing also has a compactification, which is a double lattice pet. So both these double lattice pets are compactifications both of the outer billiard systems and the square triangle. Okay. So that's sort of the underlying connection between these two things. Like that's why what happened was I was studying the outer billiards map, and I if you look at the first return map to this strip, it looks like a composition of kind of like square turning maps, but a little bit different. And then I thought to study the square turning maps because they were simpler. Okay.
Unboundedly.
So what this means, okay, so the far away from the polygon, the first return map looks nice. You have to modify, it's not quite true. You have to modify the first return map by some bounded amount. And it's equivalent in the sense that outside well, you can say it like this, like the unbounded orbits of one are the same as the unbounded orbits of the other. Like it's some kind of bounded modification which comes from some complication. So you have all these different strips, and far away from the polygon, they are pretty nice.
Yes.
And near the polygon, it's
Like this.
complicated. So you kind of change the map, but it doesn't really change the effective dynamics.
But you're concerned only this
Far
this
away
far
thing.
away, so that's enough for
That's right, that's right. The map looks very nice outside, and it's almost like you take what it looks like far away and you like analytically continue it backwards. Something like this. The way I describe this equivalence sometimes is it's what stays in Vegas. What happens in Vegas stays in Vegas. So, because imagine like you tell your wife you're going to Vegas, and you're wearing a suit, and then you're going to a business meeting, and instead you just go gambling and you do all this who knows what. But then you leave, you put on your business suit, and no one can. I'm not saying this is what I did, but there's two things that happen, and outside this kind of bounded region, they're exactly the same, and what happens on the inside is completely confined. So that's the kind of equivalence systems I'm talking about. So you make this kind of bounded surgery, and then there's a compactification, which is one of these double lattice pets. So I think these double lattice pets are nice because they should be parametrized by some higher rank symmetric space, and there ought to be like maybe a higher rank lattice or something that describes the renormalization theory or something, like in the same way that the modular group is related to the renormalization of circle rotations. And so I had the idea that studying these kind of lattice pets would lead to higher rank groups that would be like renormalization groups. But I haven't got that far. I just can do individual examples.
So compactification, so you think of a double lattice pet as a compact.
Yeah, it's compact.
Yeah.
Right. The domain is just these fundamental domains.
Fundamental.
Right. So the general thing is you're trying to understand unbounded orbits in some system, and you compactify the system, and then you want to understand the dynamics and the compactification. And the hope is that there's like a lattice acting, a renormalization lattice acting, and you can get information out of it just like people do for continued fractions or for rosy renormalization, things like that. So that's like the big picture, but I just have a small picture now. Okay, so here's the question I tried to answer while I was at the INI. So you have this complex octagonal pet. This is this four-dimensional thing with the compactification of the square turning, and you've got these two different slices that are both the renormalizable pieces. So here I'm just summarizing what I said before. And does it have a renormalization scheme? So I'm going to show you some pictures of this. So I'll just pick some parameters, like how about 411 and so in this green region here, so what I'm plotting are the periodic islands on the left. And then on the right, Okay, so okay, so I'm gonna now erase everything because I can't remember where it was. So this green region here is a candidate I found for the renormalization. When you look at the first return map to this green region here, it should be the same as what happens over here. So this on the left is the parameter 4 over 11, and this on the right is the parameter 3/4, which is the image of 4 over 11 under the Gauss map. So I just plot the pictures. So that looks good. Looks like it works. But that's bad. See, didn't quite work, but it's pretty good. See, it's not perfect, but it's not bad. Well, it sort of works. Doesn't quite work. Anyway, I started actually thinking about this in my last sabbatical 4 years ago in Oxford. And this drove me completely insane because I would be drawing these pictures and it would almost work. You'd almost see this renormalization. You can change coordinates, by the way. Like there's other slices in here. Like if I push this row of blue buttons, I can go to another slice. And this is a different slice in the same system, which is more like the octagonal pet. So in this other system, you can get a different view of these tiles. And you can also check that they almost work. It almost works. See the yellow, see that? See the yellow there? Same as that. See, the orange works, the orange works. But then here I got this. Let's see, so there's that, but it doesn't, like this piece here is not the same as this piece here. So it's not, it doesn't seem to be renormalizable, but it's like renormalizable with mistakes. Unfortunately, I can't really write a paper about that. But I fixed it here. So I'm going to explain how you fix this. I'm going to explain how you can... I found a new system which is exactly renormalizable. So I'm going to explain that in the last 10 minutes. And then that'll be that. Okay. But do you guys see what I'm doing? I'm trying to plot these orbits and I'm trying to see that if they match or not. And what I'm trying to say is that they almost match, but there's mistakes. Okay, so now I'm going to talk about pseudogroup actions. So this is a different kind of dynamical system. So the input to a pseudogroup action is a metric space, a subset of the isometry group of X, and then a domain in X. And if you think about this, the fact that it's a metric space is not important. I mean, it could be X could be any set, and isom X could be replaced by any permutation of X. But you could go crazy if you loosen the category so much. In fact, X for me is going to be R4, and D is going to be some polyhedron. Okay, so here's a new kind of system. What you do is you make a graph whose vertices are all the points of the domain, and you join 2 points by an edge if there's an element of S which maps the one point to the other. And then the orbits are the maximal components of this graph. So what's going on is that, imagine that elements of S preserved the domain. Then you could just look at the group action on the domain, and I would just be talking about the orbits. But you could imagine a more general situation where you have isometries which don't map the whole domain to itself, but you could still pick a point, and if there's some element of your set that does map you into the domain, you could call that part of the orbit. So this is sort of what you should do for orbits. This is what you should do if you have a pseudogroup action. In other words, if you have a set of generators that's trying to act on a domain but doesn't preserve the domain. This is like what the orbit means. Now, I want to talk about what I mean by an orbit tile or a periodic island. And I actually don't know of the right definition exactly, so I'll give you one definition. Morally speaking, it's like the maximal domains where the orbits have the same structure. But so let me say what definition I came up with. This page is almost identical. You can form a new graph whose vertices are the subsets of the domain, and then you join points to subsets if there's an element in the generating set which maps one to the other, and then the maximal connected components are the pseudogroup tiles. So they're like the largest regions which sort of bodily just move around under the pseudogroup and form an orbit. Okay, so this is supposed to generalize the idea of a periodic island of a pet. Okay, so now an example. I call this the D4.
Sorry, so you have to have the image superposes exactly.
Yeah,
So
So-
it sends one subset to another subset,
right.
not just up to.
Exactly.
Yeah.
So let me tell you how I got interested in this and found it. I was looking at my imperfect tiling, and I noticed that there were some approximate symmetries in this thing. It looked like some reflections. I'll just show you some pictures. Well, for these it's perfect, but like if you look at this picture, you can see that like look at the line that sort of like goes diagonally down like this. Like you can see that this is sort of a line of symmetry for the tiling, except that like this piece out here would get mapped outside. So the tiling is trying to be symmetric with respect to this line, but it's not. There's not a group action. There's a sort of a pseudo. So I looked at I drew a bunch of pictures of these tilings in this four-dimensional pet, these imperfect things, and I tried to find approximate symmetries. And eventually I noticed the pattern. And so here's the pattern. So I call this the D4 Weyl pseudogroup action. My understanding of the D4 Weyl group comes from a glance at the Wikipedia page. I think it's D4. Anyway, the space is R4, and my group, what it is it's composed of two halves. The first half is just reflections in the coordinate hyperplanes in R4. And then the other half, you take all those hyperplanes and you move them by a certain matrix, which is S over 2 times, this is a famous matrix, it's called the Hadamard matrix of size 4. It's an involution of R4. And so there's a scale, so you take all these reflections in integer hyperplanes and then you conjugate them by this Hadamard matrix, and that's the other half. So it's T union HT inverse, where H is this matrix. And then the domain is the domain for this complex octave head, which is this thing I was showing you pictures of. So S is an indiscrete group. S is a set, but the group generated by S is an indiscrete group whose linear part is this group of order 192. What is this thing? There's this beautiful 24-sided polytope in R4. It's a four-dimensional, I think this is called the D4 polytope. Might be called the A4 polytope. Anyway, and the group, there's this Weyl group, which is generated by the reflections in the normals to the faces of this polytope. So anyway, the S generates a group whose linear part is this order 192 group. Okay, so what I do, so let's investigate that. What I figured out here at the INI was how to plot these orbit tiles for this group. So let's go back to this picture. I'll take the same parameter, 7 over 11. I'll look at the second pet here. And so here's what I had before. Okay, it didn't quite work. See? Oh no, look, that one looks good. Okay, well, I'm gonna change to a different slice. I'm gonna try to make this thing fail like I did before. There. See that? It's not working. See? So this big long piece over here, it's that on the other side. But now I'm going to plot the vial pseudogroup tiles. There it is on the left. There it is on the right. Now it's perfect. In fact, I'll draw them quickly over here. Actually, let me just draw them all from scratch. So the computer, what it's drawing on the left is it's drawing, these are the vial pseudogroup orbits. You take this pseudogroup and you look at the maximal pieces. That's what it looks like on the left. And then here's what it looks like on the right. Anyway, it's exactly the same. So, and it's not just the same on the level of these tilings. If you look at it's exactly the same on the level of orbits as well. So it's a perfect renormalization scheme. The vial pseudogroup is the correct generalization. So I didn't prove it yet, but I think I know how. Okay, so let me just say, so here's the experimental fact. So for all x, the complex octopet orbit, it's contained in the pseudogroup orbit. The pseudogroup orbit is like an enhancement. So the original thing, so what it means is that all those original tiles, those gray tiles I was drawing before, each one breaks up into a finite number of these pseudogroup tiles. Like this pseudogroup system is like a refinement. It's the correct refinement. And then for these real slices where I'd already proved a renormalization theorem, the orbits of the two things coincide. So it restricts to the same thing. And then finally, the pseudogroup action admits an exact renormalization scheme with respect to the gas map. So those are all my experimentally organized facts. And then what's the punchline? What does this have to do with the square turning map? So for each irrational parameter, there's an infinite, almost everywhere defined tiling of the parallelotope that you get for this thing, this compactification thing, and all the, at least in the irrational case, all the polytopes have D4 symmetry. And then there's this irrational planar foliation, which intersects the tiling precisely in the periodic islands you get by the square turning map. So in a sense, that's the answer. What does the square turning map do? You have this four-dimensional parallelotope, and you can compute this kind of recursive tiling using the Gauss map. That's how I'm computing it on the screen. And once you have this tiling, you take this irrational plane foliation, you intersect it, and then that's the dynamics of the square turning map. I mean, that's the picture. Actually, now that I think of it, I just wrote this because to get the islands for the square turning map, you have to amalgamate some of these perfect tiles. Okay, so all right, so strictly speaking, this last page is not right, but the rest of it is right. The rest of it is right. There's this exact normalization. Okay, so anyway, that's what I did. I mean, that's what I mean. These are the things I discovered while I was here. I wanted to make my last talk with you about what I actually did at the New Institute. So that's it.
What is a complex octopet?
It's, you take the square turning map and you compactify it, and you get some four-dimensional domain, and that's what it is. It's yeah, and I mean it's I defined it in terms of these matrices on the other page. It also has some geometric description.
But is there some simple explanation of why this thing, which was originally two-dimensional, now is compactified to something that's four-dimensional? Is this like a
Yeah, let me
sphere
explain
bundle
it.
or something like that?
Well, here's the explanation. So you need two parameters to describe where you are in the first lattice.
Yeah.
And then there's two more parameters to describe where the second lattice sits with respect to the first lattice. Those four parameters determine the position in the two lattices, and that determines the local dynamics. So if you have two parameters where all those things are almost the same, then basically you can't tell the difference between the two systems in a big neighborhood. Yeah. And that's why the dimension goes up. If you look at longer words in this group, you have more widths to worry about. And so you just collect all those parameters into one map, and that completely describes. I mean, that's more or less the proof of this theorem. You just collect all the positions of all the grids relative to each other, and that gives you a complete description of the local dynamics. Yeah, that's how it works. That's why the dimension is like proportional to the word.
So the qualitative conclusions do not depend on the words.
Okay, so they do. So the group, this compactification works for the entire group. Although, for some words, what you get is not a piecewise translation. You get a piecewise affine map. And so for some words, the linear part is not the identity. So yeah, so there's a homomorphism from the group into the linear group, and then there's some infinite. I guess there's some infinite index kernel where the linear part is the infinite index kernel of that thing. Those are the words where you would expect something nice.
So you chose a particular.
Yeah. So this word is like a particularly nice word. It's in this kernel. I mean, this word at first you're like, why did I do this? But I tried all other short words and they all look like junk basically, except this one. I'd say. If you're not in this kernel, there's very few. There's only finitely many periodic points or something in the compactification. So it's somehow not that good. Yeah. Yeah.
Thomas had a comment that this looks reminds a lot of the curvature groups. So do you think it can also?
Oh, that's interesting. Oh well. You mean you might guess that this group has intermediate growth or something?
Branch
Branch groups.
Oh. So I don't know what these are. I know about these groups. Yeah, so you'd have to tell me what these groups are. Maybe afterwards. I mean, I don't. Yeah, I mean, I remember once talking to Francois Domani, and he seemed to. I can't remember the conversation so well now. It was a few years ago, but he seemed to be looking at roughly similar kinds of groups acting on the plane and some. I mean, yeah. Again, like I was motivated because again, like you might wonder like why would you think to do these square trimming maps, and that's why it looks completely random unless it comes from the study of outer billiards. Like somehow the outer billiards is closely related. So that's why I thought to do it. It's like it's a simpler, in a sense, it's like a simpler version of that. Yeah, but I didn't think about I never thought about the group theory of these things. Like are there relations? What are the relations like in the group or something? For example. Yeah. But I mean, I'm open to thinking about it.
And the result about the outer billiard follows from this discussion, the compactification. And so on.
Not exactly. It's a step. So it's a step. Like I prove various kinds of structure theorems about the orbits, and the way I prove the structure theorems is I examine properties of the compactification, but it doesn't follow logically from the compactification. I mean, in one case, in the case of the Penrose, so I studied the Penrose kite, some particular kite, famous kite, in great detail. And in that case, I found a renormalization scheme on the compactification. And so in that case, there's a proof of unbounded orbits that it's just the convective, it's, you just use the renormalization scheme in some direct way to see that there's unbounded orbits. But for, in general, I didn't. I mean, I was, probably the same kind of theorem is true. Like, you have this compactification for every parameter, and you know, there's a renormalization scheme similar for outer values. I mean, it's like I said, these double lattice pets are, you know, they're more or less parameterized by some kind of symmetric space or product of symmetric spaces or some, you know, something, because you've got lattices and fundamental domains, and you know, I wondered if there's some, maybe there's some theory that's, you know, that would just work for all of them. That's what I really want, but I just, you know, I can't. I haven't had time to, you know, make any progress on that.
The linear part is just an order 4.
Yeah.
Right. So it's just an index 4. So
Yeah, that's right. So there's, okay, good. So there's an index 4 subgroup where it's just a piecewise translation, but then when you compactify, you still might get a piecewise affine map that's not linear in the compactification. So there's an infinite index subgroup where you get a linear part. Yeah, it's a little bit curious. So I can explain the intuition. I mean, you're mapping all these squares into this kind of higher dimensional torus, but if you look at a different square, it's offset some amount. And so when you do this square turning map, it's sort of, it's affected by a piecewise affine map. And then you're taking some long composition of, you know, elements of SL and R. You know, who knows if that's going to be the identity. You know, it's exactly
but is it SL2 or SL4?
SL4. I mean, whatever the dimension of the convectification is, it's SL of that. Right. So, I forget, it's some condition like you.
Is the image a bigger?
Image of the group?
The linear part.
Oh. I don't think so. Yeah, I don't think so.
So it might be just luck that you have some.
Well, I was able to write down some condition. I'd have to look in the paper to see what it was. I mean, you sum up the exponents, and there's some condition on the. You write down the word and its generators. You take the exponents, and you know some sum has to be. Some sums have to be congruent to 0 mod 4 or something. There's some condition which I can't remember exactly what it is. If you have that condition, then you get piecewise translation and the compactification, and if not, you get a piecewise affine map.
It sounds like the linear part must be a B.
Oh, I see. If there's some condition like that. Yeah. Okay. Well, I'm gonna have to look this up and find out what it is. Oh, I see. Because there's some nice linear condition on the exponents. All right. Yeah, I'll look that up. I mean, yeah. I didn't think about this. Anyway. All right. Well, thanks for coming down.